This week, we're going to talk about parameter estimation. That is specifically, we're looking at the case where we have some data set D and we've proposed a probabilistic model that has some parameters theta. And we want to use our data set to pick some particular value for those parameters theta, which we usually call theta hat. So this is parameter estimation, estimating parameters from data. In this chapter, we're going to focus on methods that pick a point estimate for theta. That is, they pick one theta and don't think about the uncertainty about it. So by far the method we're going to focus on most is the maximum likelihood estimate. That is picking the theta with the highest likelihood on the data. So the biggest thing we're going to do this week is we're going to get a lot of practice doing this estimation on different types of probabilistic models. This is a really important thing to be able to do because almost all machine learning boils down to some kind of optimization over likelihood or something that's very close to likelihood on some training data. So we're getting a bunch of practice on that, and then we're going to talk about some sort of practical issues that come about because we're doing this point estimate rather than representing our uncertainty. Like I said, we're focusing on maximum likelihood estimation. So just a reminder, this expression here is our likelihood, probability of the data given our parameters theta. And generally, and if we're doing maximum likelihood estimation, the maximum likelihood estimate, MLE, is defined as the maximum parameters, or the parameters that give us the maximum value of this likelihood. Now, we can break this down. So first, for most of the problems that we're going to look at, we're assuming our data is IID. That is independent and identically distributed. So note that so here we've taken our likelihood and broken it down into n different terms, one for each data point. So now notice that this probability is defined on each data point. So this comes, for example, if we're doing a machine learning problem where maybe we have 1,000 examples, each one, and we're going to assume that each one is, again, IID, independent and identically distributed. So the first assumption is of independence. So note that we are multiplying all our probabilities together. I'll talk about the log in a second, but because we're using the log, we're summing them. We're summing the logs. The reason we can do this, and the reason that the other x's other than xn and the y's other than yn don't appear in this expression is because we're assuming they're independent. Then we're also assuming that they're identically distributed, and note that we're using exactly the same distribution. There's not like there's a pn here to say that this is some different distribution that we're using just for the nth example. We're using the same distribution across all the data examples. Then the other thing we almost always do is instead of maximizing the likelihood itself, I've mentioned this a few times before, instead we're going to maximize the log. Log, again, is monotonic in its argument, so maximizing the log and maximizing the likelihood itself are going to give you exactly the same answer. But the log tends to be much easier to deal with. The biggest reason is that we end up with a sum here rather than a product. And generally, lots of our mathematical tools work better for sums than they do for products. And then the last trick we're going to do is generally we take the negative of the log and minimize that. So we're going to minimize this thing. There's no particular reason for that. We could maximize the log likelihood, which, by the way, we write L of theta, same thing, just without the minus sign. Or we can minimize the negative log likelihood. This is just a convention to use one versus the other. One thing that's handy about the negative log likelihood is that probabilities are all less than 1. So the log of probabilities is always going to be negative. So if you're using just the likelihood itself, you're going to end up with a ton of negative signs all over your expressions, and it's easy to forget those. Versus if you use the negative log likelihood, they all cancel with this one. But either one works. This is just a convention to use negative log likelihood. Okay, we're going to get a bunch of practice finding the MLE on a lot of different probabilistic models. So we're going to start with a Bernoulli distribution. So just a reminder, with the Bernoulli distribution, we have our parameter theta, which is the probability that y equals 1, or the probability we get heads if we're flipping a coin. And we have a bunch of examples, y, 1 to n, values, y is either 0 or 1 for each one. So it's kind of the simplest case. I think we've done this even, but let's just do it again just for practice. So here's our negative log likelihood. This is just the standard form. So let's write in the value for what this probability is. So here I've just written in the expression for a Bernoulli distribution. I have theta to the indicator y equals 1 and 1 minus theta to the indicator y equals 0. Now let's push the log inside. So when I push the log in, the product turns to a sum, and this product turns into a addition, and the exponent comes to the front. Okay, so now I have this thing here, indicator y equals 1 times log of theta, indicator yn equals 0, log of 1 minus theta. So notice that a lot of these terms are the same. So we get this term of log theta whenever y is 1, and this term of log 1 minus theta whenever y is 0. So we can kind of simplify this by just saying how many times do we get this first term? Well, we get it n1 times, where we defined n1 to be the number of ones, and n0, same thing for zeros. So this is our expression for the negative log likelihood. We've gotten rid of the sum, which is going to make things a little easier. Okay, so now we're trying to minimize the negative log likelihood. The way we're going to do that in most cases, there are a couple different ways. The preferable way is to do it analytically, which is to take the derivative and set it to 0, which is going to find our minimum point. We're going to talk a little later about iterative methods where it's not so easy. There's no analytical form for what happens we can't analytically assign the derivative to 0 and get a solution. But in this case we can, so let's do that. So again, here's our negative log likelihood. We're taking the derivative, and here's what it is. So the derivative of log theta with respect to theta is 1 minus theta. And the derivative of 1 minus theta with respect to theta is 1 over 1 minus theta negative. So notice the negative sign is canceled out here. And here's our derivative. So now we just need to set this thing to 0. So you can do some algebra to figure out what this is. We can multiply both sides by theta times 1 minus theta. We get something like this. Let's keep going. and we get theta equals, here I'm taking the n1, putting it on the right side, and then dividing both sides by n1 plus n0, we get this, n1 over n1 plus n0 equals n1 over n, the total number of points. Okay, so this is a totally expected result. We get that our maximum likelihood estimate for theta is just the proportion of ones, which is very intuitive. Okay, good. So we're going to continue. We're going to do a bunch more examples, again, to get some practice finding maximum likelihood estimates. By the way, we're going to talk about limitations. So for example, you'll note that if we see 0 heads, we're going to get 0 as our parameter. That might be preferable, that might not be. We're going to talk about that in a little bit. Okay, let's do the same thing for the categorical distribution. So just a reminder, the categorical distribution, also called multi-Bernoulli, is the same thing as a Bernoulli, but for k options. So here I've rewritten the negative log likelihood. I did the exact same thing we did with Bernoulli, where we're using, for each of the k categories, nk log theta k. Theta k is the probability for the kth option. We can be a bit more explicit here and say k equals 1 to big K. Okay, so now let's try doing the same thing. Let's take the derivative. So now notice that here theta is a vector over k options. So we need to take the partial derivative with respect to each k. So let's do that. Our partial derivative of the negative log likelihood with respect to theta k is, notice that the only term here that has theta k is the kth term, so we can throw everything else out. We just get negative nk over theta k. Now notice that this is a little funky, right? Because we might like to set this equal to 0, but this thing, nk over theta k, these are both positive, so this thing will never be equal to 0. And in fact, our derivative will always be negative, which is to say that if we're trying to minimize the negative log likelihood, this derivative would tell us that we should just keep increasing theta k indefinitely. So now why is it? What did we do wrong? Well, we didn't do anything wrong. This is the derivative, but we forgot to take into account the fact that we have this extra constraint that sum of theta k equals to 1. We can't make all the theta k's infinite because they have to sum up to 1. So because of this fact that we have this constraint, sum of theta k equals to 1, we're not going to be able to do this quite yet. We're going to need a technique that we're going to talk about in the next chapter called the method of Lagrange multipliers. And this is a way to incorporate constraints into our optimization. So we'll show how to do that in the next chapter. Now let's move on to a univariate Gaussian. I'm not going to do the derivation here. It's not too hard. It's a good exercise for you, I think, to do it. Again, same strategy. We're going to figure out what the negative log likelihood is, take its derivative, and set it to 0. Notice that we have two parameters here. We have our mu and our sigma, which means we're going to have to take the partial derivative with respect to each one and set each one to 0 respectively. So if you do that derivation, you get a pretty intuitive result. For the mean, you get just the average of the data points, sum of 1 to n of yn, where yn is our observation, divided by n, that's just the mean of our observed data points. Our variance is just the average sum of squares of the difference of our observed data to the mean. Another way of writing it is like this. If we just take each of these squares and then we multiply out the squares, we get yn squared times mu squared times this term that we get from multiplying the 2yn mu, negative, from this negative sign here. It's not too hard to see that this term here is just equal to yn squared on average once you sum across everything. And because this is a minus 2 times that, this term and that 2 cancel out, and we get this thing here. Where y bar squared is just this same expression here, mean of y bar, and s squared is this thing, the average sum of squares, 1 over n sum of yn squared. So this shows something that's kind of handy, which is that we can get our mean and variance from what are called sufficient statistics. These values, the sum or the mean of our data and the average sum of squares, these are sufficient statistics. They're sufficient for these values, mu and sigma, in the sense that if you have these numbers, y bar and s, then you can compute the MLE, mu, and sigma. Okay, how about the multivariate Gaussian case? So for this one, we're going to need to dust off our multivariate calculus. But to start, let's just write out our log likelihood of our multivariate Gaussian. So remember, this is the multivariate case, so we have a vector of mu's and a matrix sigma, which is our covariance matrix. If we want to write out the log likelihood, we get the following. Here's our first term after we've taken the log. By the way, the textbook switches back and forth between this notation of big lambda for the inverse covariance matrix, also sometimes called the precision matrix, is a name for this matrix, inverse covariance or big lambda. So that's our first term. Here's our second term. This is just our normal Gaussian term where we've taken the log, so the exp went away, and instead we get a negative 1/2 out in front. So let's see what happens when we take the derivative. So we're going to estimate each parameter separately. So that is, we're going to take the partial derivative with respect to mu and the partial derivative with respect to sigma separately. We're going to do this as a whole vector. So notice we're taking the derivative with respect to the whole vector mu. So now we have these two terms, this first term and the second term. Notice the first term doesn't have mu anywhere in it. So for the purposes of estimating mu, that term goes away. And we just have to take the derivative with respect to this term. Also notice it's a big sum. Let's just focus on each term of the sum on its own. So we have this expression here, yn minus mu, sigma inverse yn minus mu. We can use the chain rule of calculus different than the chain rule of probability to do this. So let's define this value here, Zn equals Yn minus mu. So we can simplify this expression to be Zn sigma inverse Zn. And we're doing the chain rule because first we're going to take the derivative with respect to Zn, and then the derivative of Zn with respect to mu. Okay, so we might remember from our multivariate calculus that the derivative of this thing is the following. Sigma inverse plus sigma inverse transpose. This is a symmetric matrix, so its transpose is equal to the matrix itself. If this goes away, we get a 2 here, times Zn. And then this thing, its derivative is just negative identity matrix. So this negative sign cancels here. The identity matrix doesn't do anything here. So ultimately, this whole thing equals sigma inverse times z, which is Yn minus mu. I just cleaned up a bit here. So now recall that this was just one term of our big sum here. So let's reintroduce our sum. We get negative 1/2 sum over n of this thing here. I forgot the minus here earlier. And so the 2 goes away, the negative goes away. Notice that our sigma inverse doesn't depend on n, so we can pull that out of the sum. That's our derivative. Let's set it to 0. We can multiply both sides by sigma, so that sigma goes away, and we end up getting the intuitive result that mu equals 1 over n sum Yn. That is our MLE of our mu is just the average of our values. So this is exactly the same as what we saw in the univariate case. Just note that Yn is a vector in this case because this is a multivariate observation, and same with mu. Mu is a vector of means. We're not going to do the MLE for the sigma matrix here. It's a bit more complicated, involves a bit more multivariate calculus. Okay, so that was a bunch of practice finding the MLE by minimizing the negative log likelihood. So let's compare that to kind of the traditional or non-probabilistic machine learning strategy. So often when we're doing sort of machine learning that doesn't express itself as probabilistic machine learning, often the problem is proposed, or the problem is posed like this, in terms of the problem is posed as an empirical risk minimization problem, where we're trying to minimize this expression here. We define some loss function that depends on y for a particular example. This is a sum over all the examples. Y for the example, the parameters, and x for the example. So this could be a common thing to do is if our model takes x and theta, produces a prediction, our loss might be the squared error between Yn and that prediction. Another common thing would be is if our machine learning method just outputs a prediction of either 1 or 0, cat or not cat, it takes theta and x, produces 1 or 0, and then if that equals the label, then we give ourselves 0 loss points, and if it's 1, we get 1 loss point. That is 1 error there. So that this is a very common thing to do, just define some loss function, and when we're in a non-probabilistic scenario, we just define a loss function as something that feels intuitive. That is, the loss such that we think that that function matches kind of how bad it is to make an error in that way. Okay, notice that this looks almost identical to finding the MLE by minimizing the negative log likelihood. So this whole expression is all the same, just that we replace this term, our loss term, with specifically log of yn given theta xn. So in particular, the empirical risk minimization case is, you could think of it as just a special case of negative log likelihood, where we've chosen this specific loss function, or vice versa, our empirical or our log likelihood estimation is just a special case of empirical risk minimization, where we've chosen our loss to be the log likelihood. By the way, we need a negative sign here. I think this can be a really useful thing to realize in a couple of ways. So one is that if someone brings a loss function to you and they say, I think this is a good loss function, one way to get some intuition about what loss functions are good or better is to take the exp of that loss, or specifically the exp of the negative of that loss. Once you do that, that gives you, whoops, I just noticed we made a mistake here. That needs to be a P there. Once we do that, we get a probability distribution. That is a probability distribution for y given the output of our model. And often we can see that probabilistic distribution doesn't really make sense based on what we understand about how the data is generated. So for example, we might use squared error and a squared error loss, and that might seem reasonable. Squared error is a totally reasonable loss function. We use it all the time, so why not use it on this problem I'm looking at too? But then you might look at your data and you think, wait a minute, I know that a squared error loss function, when I take the exp of its negative, that gives me a Gaussian distribution. We talked about that last week. And maybe I know that my data is generated from something that's not at all Gaussian. One great example for that is if we're learning probability values. That is, if my output is like a predicted proportion, well, I might realize that, wait a minute, it doesn't make any sense to use a Gaussian distribution for a probability value as my output, because a Gaussian distribution goes from negative infinity to positive infinity, where probability values only go from 0 to 1. So that's one case. You can sometimes look at a loss function, and once you take the exp of its negative, then you can see it doesn't make any sense as a probabilistic distribution. Sometimes you can even go in the opposite direction. So for example, let's say my probability distribution that I'm using as my negative log likelihood is the uniform distribution. Now, if I look at what the negative log of a uniform distribution is, let's remind ourselves what that looks like. Here's my uniform distribution. Looks like 0, and then 1 over A, where A is the total length here. Once I take the log, the 0 becomes negative infinity. So that is to say, I'm giving myself a loss of negative infinity anytime my observed value falls outside my distribution. And it shouldn't be, in most situations, we don't want to be having loss values of negative infinity. That says that if we just get that one example wrong, that sort of invalidates our entire loss. It's just as well everything else could be great or everything else could be terrible, but since we got that one loss value of negative infinity, our whole loss is negative infinity. So, maybe from a probabilistic perspective, we already realized that uniform distribution was a bad idea. But sometimes it can be useful to think of this kind of like loss or score perspective for getting a sense for what a probabilistic distribution is going to encourage our model to do. Again, because often we have more intuitive for kind of losses that get added together, we have better intuition for that than we do for probabilities that we multiply together. I guess just our brains don't work all that well at understanding things that we multiply together. Okay, so the point here is just that, again, you often see machine learning problems posed as empirical risk minimization problems where we're minimizing some arbitrary loss function. It can be useful to realize that this is equivalent to minimizing the negative log likelihood and vice versa. Minimizing the negative log likelihood is just a special case of empirical risk minimization.